The floor is open to you now. Questions? Yes?
So, one of the theories was the, I believe, axion particles, correct? And you said that they were created from collisions of gamma particles, correct? And then when we detect them with, if we were to detect them with magnetic fields, we would receive, or we would detect X-ray radiation. Where's the extra energy?
You have to speak up, I can't hear.
Where's the extra energy lost between the collision of those gamma particles and the theoretical detected X-rays? Because the X-rays would be lower energy than the gamma rays.
Oh, well, they're converted into X-rays by interactions with the magnetic field inside of the detector. I'm not sure I heard
Well,
the question.
I think the question was, the energy of the gamma is higher than the energy of the X-ray. If you think about the conservation of energy principle, so if you have two gammas colliding with each other and you end up detecting X-rays, the question was, what happened to the other energy that didn't end up as a part of the X-ray? Wasn't that what?
Yeah,
Yeah.
more or less, yeah.
You guys have a good answer for
I would think that gamma rays are typically just a term anytime we use for that kind of particle, so it doesn't necessarily mean a specific energy. Classically, we think about gamma rays being a very specific energy, but we toss the term around kind of loosely to mean any particular energy. So I didn't see the exact collision that you're thinking about, but I imagine it was, when you said the word gamma ray was really just a particle of slightly different energy, not necessarily what you might 20 years ago call gamma.
But the energy of the X-ray would be related to the mass of the particle, which I think what you're asking.
I wasn't sure if there were other processes in collision, if there was any other radiation inside the sun, or if there was anything else going on. Yeah.
Other questions? Yes?
Yeah, I'm not a astrophysicist or a physicist of any kind, so I ask you to bear with me with these questions. Perhaps
We're here for you.
yeah, I may sound uneducated regarding this, but is it possible there is no dark matter detected so far because there was no dark matter? Is it possible that the issue is not that there's matter out there? If I interpret what I'm being told here correctly, that the existence of dark matter is dependent on our current understanding of the laws of gravity. Is that accurate? Is that where it started? Gravity has to, gravity, there must be matter out there because matter is what creates gravity. And the way these galaxies are moving away from each other at faster speeds, by golly, if they're doing that, there must be matter out there that's controlling that. We just can't see it, can't smell it, can't hear it, can't taste it. But it's got to be there, or else there's something wrong with the laws of gravity. Why isn't there something wrong with the laws of gravity? I mean, if you look at the concept of quantum physics, the subatomic particles, we look at these. I'm sorry, was I interrupting? Yeah. If you look at what's going on in the quantum field, again, as I understand it, there's a lot of things that happen with particles subatomically that just don't seem to fit with our classic understanding of what goes on with regular matter up here. That experiment where the photons move, and no matter how far away you put them, the polarity and all that. So my question is, just as Einstein referred to that stuff as spooky motion, wasn't really sure about what the heck was going on down there, and I'm not certain right now we're still sure of what's going on that micro level. Is it not possible that the macro level, when you're talking about galaxies and galaxies and galaxies, is it not possible that at the macro level, gravity just acts differently? I haven't heard any talk about, is there experiments being done to establish or to look for different laws of gravity at that level?
I can help with that one. So that's a great question, and let's start with something basic. So we see the sun and we see the planets orbiting the sun, and we know that they're orbiting the sun because of the gravitational force, right?
Yeah.
Okay, so now, what would happen if we saw a place where there's nothing, but we saw something going around and around it? And in that case, you would say, well, maybe there's something I don't see that's causing the gravity. And that would be a case where you can't just fix it by changing the law of gravity, because, you know, you can't see the thing. Let me back up a step. So in the case of the sun, we see the sun and the planet goes around it. And in the case of the Milky Way, the stars orbiting the galactic center, we see stuff there, we see stars there. And the stuff that's moving around, it looks like its motion is telling us that there's more mass there than we think. That's the dark matter interpretation. The other interpretation, which you're right, is a very good question, is maybe the laws of gravity are just different. And in the case of the stars orbiting the Milky Way galaxy, it's hard to tell because there is visible matter there, and maybe gravity is just behaving differently. So that's what I was trying to get to, is like, what if you had a case where there's nothing there, but something's going around and around and around? It must be attracted by mass. Now, in the case of a star orbiting like that, it could be orbiting a black hole, which is a tiny component of the dark matter. Yeah,
You have a case where there's something going around and around, and there's nothing there.
right.
What's going around and around?
Well, say like a star is orbiting a spot where you don't see anything else.
Have you seen that?
So in that case, yes, and in that case, we know it's like a star orbiting a black hole. That's not really the dark matter, but it's an example of how that could work. There's another case that we've seen where we had basically a collision of two clusters of galaxies. It's called the Bullet Cluster. And in there, so here's before, there's some dark matter, and there's some gas, and there's some stars.
Okay, but we don't know there's dark matter.
That's right. Okay, but there's a collection of material. Here's what we see is the stars and the gas, and maybe there's dark matter, maybe not. This side, stars and gas, we see it, and maybe there's dark matter, maybe not. Now here's the cool thing. These passed right through each other, and what happened is the gas got stuck in the middle because the gas interacts with the other gas, and apparently the dark matter kept going, and we can see that it's there by the way that it bends light on the other side.
You see something bending light.
Well, we see, okay, so there's a little tricky part. I said there's stars, there's gas, and there's maybe dark matter. The gas is easy to see. The galaxies, the stars are actually in galaxies, which are pretty little tiny lumps. And the little tiny lumps move right past each other. The gas gets caught up, and then the dark matter also, maybe if it's there, goes right through. And you can tell that the dark matter is there by the bending of light. And the bending of light cannot be accounted for by the amount of stars in those galaxies.
And I guess, I mean, that sounds very tautologic to me, like you're just going around and around, and you're coming right back to saying, well, there has to be gravity, that's the only thing that would make that move.
Well, no. We know, roughly speaking, how galaxies work, by which I mean, and how galaxy clusters work, by which I mean, we know the fraction of atoms that are in stars and the fraction of atoms that are not in stars in a galaxy. Okay, we know that fraction. Likewise, we know the fraction of atoms in a cluster that are part of an individual galaxy, and the atoms that are just belong to the cluster as a whole. And by far, most atoms in these systems do not belong to any one galaxy, they just belong to the clusters. And that collision which we saw, remember the pink image, that was the atoms. Almost all the atoms stopped or slowed down. And yet, and remember, the most atoms in these systems are just the gas. That slowed down, but most of the mass went right through. So there's a separation of atoms and mass. And the ideas that you're referring to, things like MOND, which some people are still looking at. There are people who are trying to understand that and are pursuing the very point you're raising. That, MOND, Modified Newtonian Dynamics.
Or modified gravity.
Yeah.
So I want to emphasize that what you're asking is an absolutely valid question, and it's something that we're trying to figure out. There are two different theories, right? Gravity is modified on galactic scales, or there's more mass than we thought and gravity is the same. And based on the preponderance of the evidence, we think there's some new kind of particle that's providing the mass. But I agree, it's a testable question, and it's important to find out.
When you say based on the preponderance of evidence, if we haven't discovered dark matter yet, what's the evidence? It's so preponderant.
So, well, we've seen it through its gravitational effects, including the bending of light.
Yeah, but see, then again, you're going back to the theory of gravity, which, and again, why couldn't gravity just be different on the large, massive scale?
Yeah.
You keep
So,
applying the same rules of gravity that we see here on Earth.
well, it's a little more complicated than that, and it's hard to fully explain it here. We'll probably just cut it short and say, based on sophisticated modeling of the way gravity works on different scales, including through the effects on the cosmic microwave background, it appears to us that there is additional matter, and it's not just a modification of the law of gravity. But I agree, it's a worthy question, and I encourage you to keep thinking about it. Let's give someone else a chance.
Please.
I'm not an academic, but I find this stuff fascinating. But I've always been intrigued by something that I have never got an answer to. Unless I'm mistaken, I believe Einstein defined gravity as a warpage of space-time. But that doesn't tell me how it works. I mean, being just an ordinary lay guy, an ex-factory worker, how would you explain the mechanics of gravity itself? I mean, the warpage of space-time doesn't really give me any details about how it works.
Rubber sheet? I'll take that one. I'll take that one. So imagine you have a trampoline, like an ordinary trampoline, and you let a bowling ball in the middle of it. Then, it funnels it down, right? A little bit. And then you could take a tennis ball and throw it into the trampoline, and it could kind of orbit around the cone shape made by the bowling ball, right? So one thing you could say is, well, the tennis ball that's orbiting around is attracted to the bowling ball, or you could say the bowling ball warps the space, making that kind of a dip, and the tennis ball just responds to the change in the shape of space. And that's a way of thinking about how the sun communicates the gravitational effect to the planets. And one cool thing about that is, in the Newtonian theory of gravity, there's a good explanation of why the planets orbit the sun, but light passing near the sun would be unaffected. Yeah, I don't know how to make less noise. There's a feedback loop, but I don't know how. Okay, there we go. All right, he's an experimentalist. So, I'm a
But I
theorist.
haven't
I'm a
found the dark
theorist.
matter
I
yet.
just identified that there was a problem. So hang on a sec. So in the Newtonian gravity, the sun basically exerts some magical force on the Earth, and the Earth feels it, and the Earth goes around. But light would just go right past. But in Einstein's theory, where the sun warps the space-time, like that analogy I gave of the bowling ball and the trampoline, even light, as it follows over that surface, would be bent. And that effect is observed. So that's one way we try to explain it. It's hard to imagine 3 dimensions warped. I can't do it either.
I mean, from a practical viewpoint, even gravity itself is a mysterious force.
Yeah. Yeah, so I totally agree. Gravity's mysterious. That's why we're working on it.
It does strange things, and the theory predicts very strange things, but every strange thing that it has predicted
Yeah.
has been measured. So, for instance, it predicts that clocks will move differently. They'll count time differently. The passage of time is different if you're here on the surface of the Earth, or if you're in an airplane or in space. And in the 1950s, people took these clocks onto airplanes.
I believe that is used in a practical sense.
Your
Yep.
GPS system.
Yeah,
Satellites.
GPS.
Yeah, so, GPS would not work if we didn't understand the special and general theory of relativity. It's pretty amazing, right?
Right.
And that's because we want the precision of, knowing where we are to, 10 meters or whatever.
Even though it's a microsecond, it adds up.
Exactly.
My Physics 3 students here remember some problems that they had to solve where they had to figure out how off would GPS be if you didn't account for general relativity.
By the way, the first two questioners both opened by saying, oh, you know, I'm not an academic or whatever, but you both had really good questions. So nobody else has to apologize for their questions, starting on from here on out.
Another thing about your question is you say, how does it really work? Well, that warping of space-time and all, that's just that tells us the framework of the equations, right? And that helps us build models and make predictions. But that's the best science can do. That just helps us predict one thing, says if we see this, that means something else. There isn't any, hey, this planet talks to the other planet, says come over here. We don't have that. All we have is a little math model that says, if my planet's here, where's it gonna be tomorrow? And that warping picture helps us picture that. It doesn't add, it doesn't mean anything's explaining. We don't really know how it works. All we have is this little idea, this math model that tells us how to make predictions.
I think we know how it works. We don't know why it is the way it
Okay,
is.
sure, we don't know why it is.
And, you know, if we didn't know how it worked so well, we wouldn't be able to make GPS work. We wouldn't be able to put a satellite, you know, sent from Earth to get to Pluto at exactly the right time and exactly the right speed and exactly the right place to be able to take photos of the surface of Pluto.
One quick other question. In the presentation, it was mentioned that gravity is one of the weaker forces.
Weakest, yes.
Compared to,
Like electricity, magnetism, and the nuclear forces.
Yeah, you take an atom, proton, or an electron going around a proton. They're pulled together, electric forces attract. They also have mass, so they pull each other together. The electric force is 10 to the 40 times stronger. So that's 140 zeros. So that's way stronger.
Yes. Okay, until all of the experiments kind of move these out, what do you think, this is probably just going to be a guess on your part, but how likely do you think it might be that more than one of the proposed hypotheses about gravity are possible?
I think it's 100% possible that it's a mixture of things.
I like the axion hypothesis, but it doesn't seem like there's enough light being generated in stars to...
And we come up with these simplest ideas. Think about us. Right? I'm sure we think we're just this tiny 5% of the energy in the universe. We're super complicated. We got protons, electrons, neutrons, but then we say dark matter is one particle. That's just a simplification so that we can, you know, have a first step. But I think it's almost 100% possible that it's a mixture of or a more complicated thing we haven't thought of.
Yes, so at the beginning of your talk, you touched on a universe of matter as opposed to a universe of antimatter. How would you describe what antimatter is?
Well, it's just like ordinary matter, except it has reverse properties, a reverse charge. And it's the kind of thing where the antimatter partner to the electron is something called the positron. And things like its mass are the same, and other intrinsic properties are the same, but its electric charge is opposite to that of electrons. And when matter meets antimatter, it annihilates into energy. Is that answering what you're asking?
So, you know, that's the whole E equals MC squared thing, or part of the story. You know, if you combine an electron with an anti-electron, people say, oh, you get pure energy. Well, what form does that pure energy take? It takes the form of 2 gamma rays, or 2 photons of light. And just, likewise, you can run that in reverse. You can put light in and you can make matter appear. I think you had a question in the back.
Yeah, so in one of the experiments, we're talking about how you have atoms sitting there. Are you waiting for them to be hit by dark matter, and then you see a light reaction, or what are you waiting? Are they going to be hit by dark matter?
Yeah.
Maybe repeat the question.
I think the question is, what are you doing in order to let some targets be hit by dark matter and you said something about waiting for light from them. So I think you're referring to, for example, the LZ experiment that I talked about, where they've prepared ordinary atoms, xenon atoms, in a state so that if they were bumped by dark matter, they emit light. And they also ionize nearby atoms, and they take those electrons and with an electric field and drift them up to a place where there's gas, and that creates a second flash of light. And by looking at the different combinations of the strengths and timing of those flashes of light, you can tell whether it was dark matter that hit it or some type of radioactive background. They have seen light flashes. Thus far, no one has seen evidence for dark matter from that, though. They've seen evidence for background, which they've been able to very clearly identify as such. But none of the experiments have incontrovertible evidence for dark matter. But let me step back from that a moment and say there are a number of experiments which have had potential signals, what looked at the time at least like potential signals of dark matter. Thus far, each of those signals has been different from the other. That is, the dark matter candidates that could have made those signals were different from each other. And no one has been able to reproduce the strongest, the most long-lived evidence for dark matter, which came from a crystal-based experiment, which I didn't describe. So they have a signal, and in some ways it behaves like dark matter. But in order to accept evidence that you've seen something extraordinary, whose properties we really don't know, you need to be able to reproduce the results by different people using different techniques. So far, no one has been able to do that.
I could be wrong on this, but at CERN, do they use lead ions to look? Is that the dark matter still that they use lead? No.
They're not looking. Oh, sorry.
I mean, there is an experiment at CERN to collide heavy nuclei with other heavy nuclei. It's not for dark matter, it's just because it's cool.
Are they doing experiments into dark matter at CERN at all? No.
There is one axion experiment there.
Plus,
And
their
proton.
proton collisions
Right.
are searches for dark matter as well. That's a
Actually,
multi-purpose.
Adam should talk about it.
You're right. Yeah.
The collider search.
Yeah, this was mentioned. One thing that you can possibly do is, if dark matter talks to us, collide two protons, smash them together, make dark matter. Thing is, what would that look like? Well, you'd have one particle come in, one particle come out, and you would make nothing. That would look a lot like the two particles just missed each other. So usually what they look for is two particles have to sort of bounce off something else. So you make something that you see, one of the particles that we know, and you look for nothing coming the other way, because that's going to look really strange. Two particles come in, something goes flying off in this direction, nothing goes the other way. So they look for that, and they can use that as a way of testing how strongly something would...
So that would look like a violation of conservation of matter?
Absolutely right, yeah. And the reason they do it with protons is they can sort of get more oomph into a one particle. If you do it with lead, you have to spread that oomph over the whole lead nucleus. So the individual things in the lead aren't going nearly as fast or as energetic. So it's more efficient to do it with protons.
So for the liquid xenon student, why are they using xenon atoms?
Well, that's, okay, so the question is why use xenon atoms to look for dark matter? And one detail that I didn't go into is the selection of targets. In addition to, you saw that long list of theories and the long list of candidate particles that come out of those theories. Well, each of those candidate particles would, if it exists, interact with matter in a different way. And so all the targets that are chosen to emphasize the search for one of those types of candidates. So the type of candidate that they're looking for in the LZ experiment is one which interacts with the nucleus as a whole. And there, the effective size grows as the square of the number of protons and neutrons in the nucleus. So you want a big, heavy nucleus. There are other experiments like ours, which are looking for a different candidate, which interacts with something called the spin of the nucleus. And there you want to have individual protons or neutrons in the nucleus that are ideally suited for looking for that type of candidate. So each type of target particle is selected because it's probing one candidate dark matter, or ideally you'll choose targets that search for multiple candidates. But those are the kinds of considerations that go into selecting a target atom. Yes, because of its mass. So they're looking for it with a large number of neutrons and protons in there. We used to do the same. Right now we use one fluid, which is a firefighting fluid, C3F8. The fluorine atom happens to be very good for looking for dark matter that would interact with the spin of a nucleus. But we used to use a different chemical, CF3I, another firefighting chemical. And we used that because the iodine atom has so many protons and neutrons in it, 127. And so the chance of interacting with dark matter that looks at the nucleus as a whole would be greater for iodine than fluorine. So you choose your targets based on the type of candidates you're testing.
I mean, there's also a lot of practical considerations. You can make a large vat of clear liquid with all of these things, as opposed to, say, like a bucket of lead. So, you know, those kinds of things and the rejection of backgrounds go into what you can do, because the whole point about the detector is it has to be huge, and if it makes a little flash of light, you want to be able to see it, so it needs to be clear, and you know, there you go. That kind of thing builds it up. What you in the front there?
Yeah, I have two questions mixed together. What would you say is your favorite thing about being a theoretical physicist, and in your career, what has been your biggest accomplishment?
The question is, what's my favorite thing about being a theoretical physicist?
I'll take that.
Go for it. And what's the biggest accomplishment? My favorite thing is I think this stuff is fascinating, and I get to think about it every day. So that, I think, and I hope to continue to do it as long as I, stay employed. Biggest accomplishment? I don't know. I don't know. If I'm being a theoretical physicist, I get to be wrong lots of time and think about some crazy thing and say, oh, hey, maybe this is what's going on, and explain something. I guess, lots of accomplishments. I guess the thing I like most is having an impact on the experiment. So convincing somebody who's working on an experiment, dark matter experiment, collider experiment, saying, hey, this idea is good enough, go out and look for it. And somebody does. And most of the time it gets crossed off as not right, and it's cool that I can be not right all the time. But it means, I think science is advancing that way. We're learning something. It might be slow, not this, not this, not this, but stuff is going forward. So that's my take. But
Good question.
you're not going to answer that one? You're a theoretical physicist, too.
If you guys have different experiences, I like
No, I pretty much agree with that. It's a good question. There was a guy in the back there.
I was wondering if when you look at the different galaxies, if the dark matter content is the same in all of them, or if there's some galaxies that have higher or lower contents of dark matter?
Yeah. So that's a great question. The question was, do all galaxies have the same amount of dark matter, if they do have dark matter? So it appears, no. It appears that there are some galaxies that, let's say we think we have this much dark matter. So like say this is a certain amount, and here's the same certain amount. Some of these galaxies have a pretty large number of stars, like the Milky Way. But then there's some other galaxies that have, we think, a similar amount of dark matter, but many fewer stars. And one of the interesting things to try to understand about the way the universe works is, why is that different? There should be, well, it's interesting to ask, why is it different? Why is it almost the same? So that's part of what we're trying to figure out of, you know, we don't want just the, so if you ever buy a can of like soup or whatever, it lists the ingredients on the back. And that's sort of where we are with the universe. We know it's, 74% this and 24% blah, blah, all that stuff. It doesn't give you the recipe. So the thing we're trying to figure out, first we have to get the ingredients list, and then we want to try to reverse engineer the recipe of how things get put together and why they look the way they do. Because with those same ingredients, I guarantee I could make something that tastes a lot worse.
Yeah, I was wondering, based on the standard model explaining matter, it sounds like for dark matter, that the standard model won't work, that you need different type of things. I'd like you to comment about that. And the other question is about dark energy. When we're talking about dark matter, and I'm reading up for this, I kept coming on this dark energy.
So the question is, we got a standard model. How does dark matter fit into that? I guess is question number one. And the second one is, how does this dark energy fit into it? Those are good questions. So first of all, the way I think about standard models is kind of like our periodic table. Periodic table was set up in 1800. You got your helium, hydrogen, et cetera, et cetera. Those were the building blocks at the time. Everything was made out of that stuff. Well, we've smashed stuff together a lot harder, and now our periodic table is the standard model. But when people had, 100 elements in that periodic table, they didn't stop. They kept looking for new stuff. And the reason that they thought was the new stuff was there was stuff that they couldn't explain with only their 100 elements. That's exactly the stage we're at right now. We got a bunch of stuff we can explain with our standard model. Dark matter is not in that. So we got to extend it. And that's one of the things that's really exciting. If we were done, nothing left to do. We've figured it all out. But we're not at that stage, not even close. We know that there's stuff we don't understand. So what we try and do is we try and do 1,000 different experiments saying, well, maybe it's kind of like this, maybe it's kind of like this. And that's going to allow us, hopefully one day, to figure out what is that extra element to put in our new periodic table. And then we'll go from there, look for the next new thing. Now, dark energy is very different. All the stuff, matter, that we've talked about so far, that all clumps together. You put it, and it's going to start clumped together. If I make a bigger box and I have the same amount of matter, that matter's more dilute, it's more spread out, right? If I have 3 water bottles on this table, if I put in 9 tables and I keep only 3 water bottles, I have fewer water bottles per table. Right? Dark energy doesn't work that way. It's like me expanding a new table and putting a new water bottle. Every time I expand space, I get more dark energy, more and more and more. So it's totally different. It's not matter at all. It doesn't clump together. It's just sort of a constant amount. I keep expanding, I keep getting more of this stuff. So it's not a particle at all, which means it's really weird. It totally blows my mind that we think 74% of the universe is completely alien compared to the stuff that we know as matter. So we know nothing about it. So dark matter, we say, okay, that's probably a little particle, something that would clump together, something that would get less dense if I put the same amount in a bigger amount of space. Dark energy is not like that at all. So we know zero about it. All we know is it is not like matter.
But if they talk about the dark energy fueling the expansion of the universe, so how does that fit in? What would be driving it?
Well, it still has energy associated with it.
Not the energy wasn't normal.
Exactly. A totally different type of energy. So we can write down, usually we think about energy as being energy that it costs to make this thing, energy that would be put it in if I throw it. Dark matter, dark energy is a third different kind of energy. It makes it, fascinating and totally frustrating because we only know how to study, matter kind of stuff.
When you talk about dark energy, the whole concept of a photon is alien.
Absolutely. Yep, it's a different type of energy completely.
So it's going to be some light particle like a photon?
It's not a particle. Yeah, it's not a particle. No. If it was a particle, it's part of the thing that's difficult about it, because if it was a particle, we know how to study particles. You smash other particles into it, you study how it bounces off, how to react. Dark energy, it's not a particle. You can't do that.
So you can't detect it at all at this point?
We can't detect it on a small scale. You can see how it impacts things on a big scale. But
To explain the expansion of the universe?
Pardon me?
You say you're using it to explain the expansion of the universe?
So, it's used to explain the acceleration of the expansion. Just to explain the expansion, doesn't need dark energy, but to explain the fact that it's speeding up does. So, actually, I have a question for you, sort of. I want to say it's fun. I'm visiting town for the day, and it's fun for me to come to an event like this and see something like more than 100 people who are interested about learning more about physics, and I think that's really great. And I want to ask you all to just wave high. So I've never taken a picture from the stage before, so I just thought I'd see what it was like. And, another thing I want to highlight is, I think you're fortunate, and our, field of physics is fortunate to have people like Dr. Levine who are both, experts in the physics. I mean, he probably soft-pedaled it, but he's, a world-renowned expert at making these dark matter detectors work. But the other cool thing about him is that he's really committed to bringing that science to the public. And I think, like I said, the field of physics is lucky to have him, and I think South Bend's lucky to have him too. So let's thank you. This guy, he works for the other school, so let's not talk about it. Oh, he's a good guy too.
Any questions?
Yeah. He's back.
We still didn't figure it out.
Yeah, it's only been like 20 minutes.
20 minutes!
Yeah.
That you're looking for dark matter as such a tiny, tiny, tiny thing. Is it safe to presume that all the theories say that dark matter is subatomic, neutrino size?
No. No, actually. No, primordial black holes.
Yeah, no, I talked about black holes. Those were from the ad hoc class of ideas, those black holes made in the very early universe.
Yeah.
And those could be the size of asteroids. Now, we do have limits on, we know the black holes can't be very, very big, because we would have seen them, I didn't talk about this, we would have seen them in searches in the Milky Way for evidence of them passing in front of other stars, and from the gravitational lensing that Dr. Beacom talked about, on the large scale, we would have seen it in the small scale in the Milky Way. So we know they can't be too big. We also know they can't be too small, because one of the things that we know, thanks to Dr. Hawking, is that very small black holes evaporate and explode into light. So we have limits on the candidates of dark matter that could be that could be much larger than a single particle. And if you looked on my graph, black holes were really up there. Those were pretty large, but that's why that scale of possible value for dark matter particles was so very large.
So what's that, a range again?
Trillion.
Yeah. So it's possible that dark matter has a fairly large mass because of, say, black holes or whatever.
If it does, there's none here.
Well, that's right. So there's none here right now, and we'll never in that case, we wouldn't find it in an underground detector or at a collider or whatever. We would have to find it some other way.
So in addressing that particular theory, if dark matter is these little black holes, it would be much, much bigger than something the size of a neutrino.
Yeah.
There would be none of them in our galaxy.
Well, they would be in our galaxy.
But there wouldn't be one in this room.
Wouldn't be one in this room?
The bigger the mass of any individual dark matter candidate, the
Right.
fewer of them there are. So they would still be a large number, say, in the Milky Way galaxy, because we know that dark matter is spread smoothly throughout. It's not clumped like at the center. So astronomers are actually looking for candidates like this too. If a dark matter asteroid, say, goes through a star, they look for flickering in starlight. That would be a signal of a black hole hitting a star. So that is something that's being looked for. But I don't know if I intentionally or not, sort of demoted that as a somewhat ad hoc idea, because it was invented just to explain dark matter, and there's no particular reason people have come up with why the universe, or a mechanism that people would have come up with to produce such a thing.
Yeah, but when did you start thinking the theorists were right?
Well, I just spent the last 15 years looking for dark matter that has been predicted by other theorists, so I'm not blaming you guys, that we haven't found.
We have to keep an open mind and search in different ways.
It could be any one of the things on that long list, a combination of them, as you were suggesting, or it could be something no one's thought of yet.
So if it were anything bigger than this neutrino-sized piece of dark matter for which you search, we'd see them much more easily? Why
Not
wouldn't they be
necessarily.
here? If they're all over the universe,
Yeah.
why wouldn't they be in this room, or at least on this planet, or at least in our solar system? We could see them out there banging around.
They
Well,
could
okay,
be.
let's put it together this way. Suppose there's, let's see, suppose there's 1 million euros of currency in South Bend. So European currency, 1 million of them. And we don't know if there's 1 million €1 notes hanging around and everybody's got several of them, or nobody's got any of them except one person has a single note that's worth €1 million. But we do know the total amount. So in a similar way, we know the total amount of dark matter mass in the galaxy. And as Elon said, if we say the mass per particle is small, there's a gazillion of them. If we say the mass per particle is large, there's fewer of them. And then, so maybe there's not, if there are few, maybe there's not one in this room on average, but there has to be a certain amount to make up the known mass.
So the only way we can look for them is by presuming they're tiny, then we know they're here and we can see
Yeah,
them.
so the tiny ones can be detected in the underground detectors and things like that. If you make them more and more massive, then they would be too rare. You're quite right, and it would never pass through his detector. But then there's other ways to find those.
And astronomers are looking for that.
Right, right.
But there you have to look at the 400 billion stars in the Milky Way galaxy and looking for the flickering that I was talking about from these effects.
So if there's one particle of dark matter in my hand, like that was the analogy, so how can we not detect it in a detector if we know there is one in my hand?
Yeah, go ahead.
So when you detect something, when you detect sunlight, you're feeling a photon that stops on your face and transfers its energy to your skin. If you have a particle, so the question is, if you've got a particle on average in your hand, how come we don't see it? How come we don't feel it? How come we don't catch it? Well, in order to catch it, you have to be able to stop it and transfer its energy to you. But one of the properties of dark matter is that it interacts so very weakly, i.e. rarely, that it just goes through your hands. So it's not like you're holding on to the dark matter particle, it's just passing through the space that your fist resides in at that moment, but you're not catching the dark matter particle. Now, it sounds like an impossible idea, but if you hold out your thumb every second, 100 billion neutrinos from the sun go through your thumb. You don't feel them because they also interact only weakly with your body. And so you don't sense them, and you need very, very special sensitive detectors like the SNOW experiment, which we saw. That's what I worked on before, looking for dark matter. And there we had 1 million liters of heavy water to detect about 20 neutrinos per day when you get 100 billion per second through this small area. So that gives you perhaps a sense of how rare the interactions are and how you can have it in your hand and not feel it.
So, one way to think about it is, as Elon was saying, if you see photons that are coming right from you can't see into my hand, right? You don't know if I'm an alien human hybrid or whatever, or for flesh and bone, right? But with X-rays, you can see through, and the X-rays mostly get through, but some of them scatter. And now imagine something that scatters even less, and then you're on your way to thinking about dark matter. You did.
Don't need you guys anymore.
So you talked about basically there's dark matter in all the galaxies and whatnot. So we know that there's some here, and you used your analogy with the Euro and South Bend. Well, do we know how dark matter interacts with itself at all, and if it has any kind of structure to it that could help us maybe narrow down our search area?
Easy easy answer is no, we don't know.
The only thing we know for sure is that it is massive, so it experiences gravity. Like I said, it clumps together, pulls other stuff that have mass. But it could have other interactions too. Lots of people think about this, think about the implications it would have.
Like, so what if the dark matter sector has many different particles in it, like you talked about
Yeah,
earlier?
that totally
So
allowed.
those could be interacting strongly with each other.
Sure.
So there could be like a whole world of dark matter particles, sort of analogous to our own, where they interact strongly with each other and make dark atoms and dark planets and all of that stuff. But we don't think so, but it's a possibility.
So is that where our idea of dimensions comes from?
No. Yeah, that's just different.
Kind of different.
And so could that be related to the Bullet cluster? How like it seems like the clumps of dark matter travel, it's like they're interacting with each other and they stay with each other as the two galaxies pass through each other?
Absolutely. The bullet cluster is one of the things that people use to set limits on exactly how strongly dark matter could talk to itself. Absolutely.
Because the two dark matter clumps
Yeah,
went
they
right
go
through each other.
Go right through each other.
But you're asking a separate thing is why is it a clump? And that's due to gravity, not due to scattering.
The dark matter is also traveling with all the galaxies that were in those clusters. They also pass right through, and they're coincident with the dark matter. It's just the unaligned or unbound individual atoms that have been left behind, but all those galaxies passed right through with the dark matter. And it's gravity, but scientists are definitely looking at these different possible rich interactions between dark matter. And you have all sorts of names that are analogous to names for particles that exist in ordinary matter, like dark photons.
There's one more question. Why don't we maybe wrap up and
Please.
go to your demos
Yeah.
in the back? Go ahead in the back.
If dark matter can interact even weakly with our particles, where it would bump a particle and impart some energy, and then we could see that, would the dark matter then lose energy, and then eventually all dark matter would fall into the center of the gravity over time?
That's an awesome point, and it's correct. And the reason that doesn't happen is that the dark matter scattering is so rare. That's one of the ways that we know that the dark matter scattering probability has to be very low.
What I think we should do now, first of all, let's thank our two guests who've taken time out of a very busy schedule to join us and answer our questions today. Dr. Adam Martin from the University of Notre Dame and Dr. John Beacom from The Ohio State University. And thank you all for coming out here. Now, I'll be happy to stick around and answer questions one-on-one, but I also want to point out that in the back, my students have set up some interactive displays where you can see certain things that we do in the lab to help us in our search for dark matter, including some of the broader impacts. We're helping a local luthier understand how to model jazz archtop guitars. In fact, Tom, if you wouldn't mind standing up, Tom Nania founded the House of Luthiery after graduating from IU South Bend in, was it 2012? 2012, and has founded a luthiery here and has been engaging in scientific study of instruments to be able to do something similar to what people have been doing since the 1960s with violins that have been able to reproduce violins that are acoustically identical to the Stradivarius line of violins. He's trying to do the same thing with guitars, and we're working together trying to help him with that. And so he's got some displays back there, as well as, I guess, Nathan Walkowski is back there. He'll demonstrate some of the other acoustic stuff that we're doing in support of the dark matter experiment. And I'll also be happy to stay and answer questions. But I think Dr. Martin and Dr. Beacom have already had a very long day, and I very much appreciate your sharing your expertise with us.
Happy to be here, and I want to thank everybody for their great questions and especially for their interest in science. Thanks.